I'm Dr. T and welcome to my whiteboard. Today we're looking at a percent yield question for a limiting reagent problem. This is really going to highlight most of the features of stoichiometric reactions and doing chemical accounting that we normally do as chemists. So this is going to cover a lot of it. You may be dealing with the whole kit and caboodle, or you might be dealing with only parts of this. But if you can do the whole, you can do the parts. So let's look at the information we have to start with. So presumably the question here is that we've got a reaction that we've done. We have taken 23.2 grams of ferric oxide, reacted it with 10.3 grams of aluminum. This is a good old thermite reaction. I have the balanced equation up here, and you're going to need the balanced chemical equation. So go ahead, check out the video on balancing chemical equations if you're uncomfortable with those. So first things off, I'm going to need that. I also need one more piece of information for a percent yield equation. Percent yield is going to involve how much I actually get. So I need to get what I call the actual yield, and that's going to be this number. So this question says it yields 12.2 grams of iron. So it's either going to have to be provided in the question, or I'm actually going to have to do the reaction, and I'm going to have to weigh out this iron. So either way, whether it's done experimentally or simply included in the question, I'm going to get this percent yield starting with what I call my actual yield, what I actually get. And that's actually the easiest part, well, unless you're doing it in the lab. Now, the next part that I'm going to need, because I actually need to do this equation over here. I'm going to take my actual yield, and I'm going to divide it by what I call my theoretical yield. And that's if everything went perfectly, how much could I get starting with this amount of stuff? Obviously, I can't get more out than I put in, so I need to figure out how much I could get out given the amount of stuff I put in. Now, it's not the sum of my two reactants. Instead, it's going to be how much I can theoretically get. The reason it's not the sum is it's very likely that some of one or more of my reactants will be left over. So I get to do a couple of things. One, figure out how much of which one is left over. So to do this, I'm going to do what's known as a theoretical yield calculation. And I need a little bit more information. Specifically some formula weights, or molar masses, depends on what you wish to call them, for all the players involved. In this case, it's going to be ferric oxide, aluminum, and iron. I'm not really looking at the aluminum oxide, so I don't really need to deal with it. Now, I'm going to set up a couple equations. Those are going to be here. The first one is starting with the ferric oxide. I'm going to start with this one. I'm going to convert it into moles. So I'm going to go with the amount that I have. In this case, it's in grams. I'm going to go to moles. So now I have moles of ferric oxide. Then I'm going to use my balanced chemical equation. I'm going to pull the coefficients off of this. I have a 2 for the iron and an invisible 1 for the ferric oxide, so 2 and a 1. Then, now that I am in iron, I've transitioned from ferric oxide to iron. I'm in moles of iron. I'm going to convert to grams of iron, and that's going to give me a yield. Now, at this point, I don't actually know if this is my theoretical yield. Spoilers, it is, but I'm not for sure, because it could be that there could be leftover ferric oxide. In that case, this won't be my theoretical yield. My theoretical yield will be lower. So I need to do this entire equation all over again with my other reagent. In this case, my aluminum. So I'm going to do the exact same thing. I've got my aluminum. I convert the aluminum from grams to moles. As chemists, we always work in moles. So we're going to go from whatever we have to moles, and then back to whatever we want it to be. So moles are usually in the middle. Okay, so I'm going to go from grams of aluminum to moles of aluminum, and then from moles of aluminum, I'm going to convert that using my coefficients, the 2 in front of the iron and the 2 in front of the aluminum, to moles of iron. And hey, this should look like the one above. I'm going to convert from moles of iron to grams of iron, and I get another potential theoretical yield. Now, this is where what we call limiting reagent comes in. If I do this reaction, one of these two reagents is going to run out first. The question is which one? Well, I look at these two potential theoretical yields. The one that's going to run out first is going to give us the least amount of stuff. So I know that whichever one of these two numbers is lowest, that one, is going to be our limiting reagent. So this is our true theoretical yield. This one doesn't represent reality, because in order to get this number, I would have to have more of the ferric oxide than what I have. My aluminum is said to be in excess. I have more aluminum than I need to react my ferric oxide, and my ferric oxide is what's going to limit my theoretical yield, so it is the limiting reagent. Okay, so now that I've determined my limiting reagent, I can then go ahead. That tells me my theoretical yield. My theoretical yield goes down here. Boom, boom. And I can calculate what is known as my percent yield. This is how much I got compared to how much I theoretically could have obtained. Depending on context, depends on the value judgments. There are some contexts where you got something, that's good. Others where if you got 99.9% theoretical yield, that's not good, that's not enough. It just depends on your reactions. Okay, so this is limiting reagents with percent yield. There's one more thing we can do with limiting reagents, and that is we can figure out the amount of the excess reagents that is left over. So if you remember last time, we calculated a percent yield, and in order to do that, we found the theoretical yield from our iron oxide was 16.2 grams of iron. We also found that the theoretical yield from our aluminum was 21.3 grams of iron, and because that number is higher, then we are able to say that the aluminum is in excess and that the true theoretical yield would be this 16.2 grams of iron. Well, with this information, we can calculate how much aluminum we should still have left over. So for starters, what we need to do is figure out how much iron we're not making because the theoretical yield is being governed by the iron oxide instead of the aluminum. So this is the difference between our proposed aluminum theoretical yield and our true theoretical yield, which is governed by the iron oxide, or iron 3 oxide. And that's going to be 5.1 grams of iron. Okay, now what we're going to do is the same stoichiometry. We're going to do the same conversion that we've done beforehand, but instead of going forward from reactant to product, we're actually going to go from product to reactant. When doing the stoichiometry, we can go from reactant to product, product to reactant, product to product, or reactant to reactant. All we end up doing is simply swapping out which symbols and which coefficients we want to use. So in this case, we're going to go from product to reactant. So I have the amount of iron I didn't make that I could have made had I had sufficient amount of iron oxide, or if it was the one that was in excess. Now, so I'm going to convert this difference, convert the moles, figure out how much aluminum was not used in making that amount of iron oxide, or that amount of iron from the iron oxide, and that is my excess reagent left over. Fairly straightforward. It's just an extension of the previous concept. With that said, have a wonderful day.